Share according to the cloud. Check. Second thing, I kind of, oh, didn't go nuts or anything, but I changed up our Moodle page a little bit. Sometimes I just find that it gets a little bit weird in the beginning. So anyways, so I put the course outline up top. The link to the YouTube videos is there at the top as well. So it'll just be my page, and then you'll just have to find whatever video you're looking for. And then the WebAssign link, you can just as easily just go to webassign.net and then sign in that way. But the link just makes it easier. And then our classroom link, and then our meeting ID if you prefer that. I keep trying to scroll on this computer, but it's on this one. And then we had week 1, that was last week. That was just for fun. And then week 2, that's where we are now. We're gonna start talking about sets. So chapter 2 in the textbook, hopefully you've had a chance to kind of poke around. There's not a lot on WebAssign yet. Or I did post some stuff earlier today. So you'll see that there's chapter 2 assignments. There's actually one for each section. So you'll have, and they're due on Friday next week at essentially midnight, 11:59. So there's no confusion. Okay. And then I also put the classroom link there, which I'll probably remove because it's a little bit, it's a lot because it's up at the top. But anyways, just so you'd know where to find me. So I'll just show you.
I think you could let it stay just to get as much information as possible.
Wait, let me turn up my volume here. Say that again.
I'm saying I think you could let it stay just to get as much information as possible. For the link.
Yeah.
I was saying I think it's probably okay to stay if you let it stay there if you just to get as much information as possible.
Oh yeah. Yeah. Well, yeah, I've got it up here at the top too. So don't worry. It's around.
Okay.
Yeah, don't worry, it's there. It's there. Let's see here. I wanted to show you this one. What I did there. Okay. You guys are here, and if I open student view.
Where exactly is the textbook?
The textbook is in WebAssign.
My ebook, is that what it is? Is that the text? Oh.
Yeah. If you go down to the bottom, I think on my desktop it's the bottom right-hand corner, but on my iPad it's at the very bottom. So they make you work for it. You have to scroll all the way to the bottom, but then there it is. So you've got the getting started with WebAssign. I saw a lot of you had already done it. Yeah, bottom right. So it depends if you're on like a tablet or a desktop, but. So the getting started is just getting used to using WebAssign. And then you've got homework for 2.1, 2.2, 2.3, and 2.4. I posted those already. Today we're just going to go through 2.1 and 2.2, kind of see where we get to. And then next day we'll do 2.3 and 2.4. And so hopefully we'll have these all finished. And if we don't finish, I'll adjust the due date so you'll have more time. But right now I'm just making them due next Friday at, oh, it looks like it's doing Edmonton time. So I'm gonna have to change that, but confusing. I'll change it to midnight your time, okay? All right, so good. Good, good, good. So now you've got some stuff there at least to work with. All right. So, oh, and I should say, because I'm recording the video and I want to have my face in there because I do this a lot, right? Sets, subsets. If you do end up speaking in the video, then it will be recorded as well. And if you've got your camera on, then it will show your face. So just, if you don't want either of those, you can chat in the chat box. I'm getting better at checking it and reading it. You too. Exactly. Well, I don't think they'll see your chats. No, they won't. Anyways, so just if you're speaking, it'll show you. But if you're not speaking, then it doesn't show you. Okay. Hey, what's going on with my blank page here? Oh, it's thinking about it. Of course. I can just start a freshie. Whoa. I don't think it's gonna like having this thing. I'll change that later. All right, so like I said, this week we're going to talk about sets and kind of just set theory. There's a lot of definitions, and we need to know about sets and just kind of how sets work for all of math, essentially. So let's hop to it. All right, so we're going to do section 2.1 first, of course. Sets, subsets, and Venn diagrams. So nothing kind of crazy, but there are a lot of definitions that we need to pay attention to. Okay. And just kind of work with. So nothing crazy, but if we go back to kind of this is a puzzle course, well, we need to know the rules of the game before we get started. So the rules are kind of boring. But a set, and we learn about sets just kind of as a foundation of everything, right? A set is just a collection of things or a collection of elements. So a set would be the letters in the English alphabet, for example, all our numbers, dog breeds, those are all sets, right? And there are elements within those sets that we can talk about, right? So a set is just a collection of objects. A collection of objects. So we can define sets in two different ways. We can define them just by describing the set, right? So if I say, oh, it's a set of all the dog breeds, then we understand what that set is, right? Or we can do the roster method, which is when you list every element in there. There's kind of a cap to how large that set can be, right? But very common that we just list all the elements within a set. And so sets can be defined in two ways. And like I said, in case you didn't see, because the notes from last day, let me jump around just a little bit. We're just getting to know each other anyways. Here on your Moodle page, I just post your notes like this, right? So you'll have these notes that we're writing. So if you find that it's easier, I know a lot of people find it easier to just kind of sit back and listen and not have to keep up with all the notes. So they will be available after class, okay? Just so you know. Okay, so sets can be defined in two ways. The description method, or the roster method. So the description method requires that we describe the set in a way so that it's clear exactly which elements would belong in the set, right? So if I said just dogs, am I talking about, you know, Bowser and Maggie and Bella, right? Or am I talking about dog breeds, or am I talking about, so that would be not a very good description of a set, right? But the description method, you have to describe the set in a way that we know exactly which elements belong to it. In a way that we know exactly which elements belong to it. So what we were talking about, right, in order to know exactly which elements belong in it, right, another way to say that is to say that a set is well defined, right? And so we have a well-defined set if it's very clear what belongs in the set. So a set is well defined if it can be clearly determined which elements belong in the set, right? So kind of saying the same thing a couple of different ways, but I'll underline kind of the definitions, or try to. A set is well defined if it can be clearly determined which elements belong in a set. Belong in a set. So just throwing some underline in there, right? Because now we're talking about, okay, well, if a set is well defined, right? And so the description method has to have essentially a well-defined set. The roster method simply lists all the elements of the set. Lists the elements of the set. I'd say most often in our examples, I'm just gonna give you the set using the roster method, right? But there are some times when we could just describe it. So the elements, right? So everything in the set, those are our elements. So the objects in a set, the objects in a set are called, sometimes they're called members, but usually I would just call them elements, right? Are called members or elements. So these sets are usually defined by capital letters. I don't know, have you guys dealt with sets before? Kind of a, probably, I'm guessing mostly no, right? And if you have, then whoop-de-doo, you get an easy day, easy week. No big deal there. But I was just curious. Sometimes there's a lot of overlap in courses, but if we're all just starting out, then it's good. So the objects in a set we're going to call them elements, right? And so sets are usually denoted by capital letters, and that's kind of across all industries. So sets are usually denoted, and there are few exceptions, are usually denoted by capital letters. Okay. So something like capital A might be my go-to set name. A, I'll define, and a set, we wrap it up in curly brackets, right? Just to show that this is a set. And so my curly bracket, my left curly bracket is always just beautiful. My right curly bracket, not so much. So if we let A be the set of numbers 2, 4, 6, and 8, hey, not bad for my right curly bracket. We can describe this set, right? Even numbers, even whole numbers between 2 and 8, right? This is just shorter, right? So we've got the description method or the roster method. This would be the roster method, where we're just listing explicitly all the elements in the set. And let's define another element, or another set, sorry. B is going to be all the odd numbers, 1, 3, 5, up to 7, and 7. Doesn't really matter, but just so you don't go to that. So these, right, tell us that we have a set, kind of set notation. In set theory, we have all these shorthands, right? Instead of having to write, 2 is in the set A, right? We've got shorthand for that. So today we're just gonna plow through all this shorthand. We'll introduce more as we go, but first day is always kind of tough because it's all definitions and all that stuff. So we use kind of a C with a line through it to make an E, to say in the set, to denote elements in a set. Oops. Okay. So for example, we would write the number 2 is in the set A. Right? And just as you probably figured, but 2 is not in the set B. Right? The element 2 is not in the set B, because B only has 1, 3, 5, and 7. Right? So you can read it as in the set or just in. 2 is in A, 2 is not in B, right? And so kind of even more shorthand, you could just say in the set. Right? It's understood that A is a set. So here, 2 is in the set A, or we could write 2 is in A. But that's probably just me being sloppy. Right? But we get lazy. Or similarly, right, 2 is not in the set B. Or 2 is not in B, where it's understood that A and B are sets. Any questions so far? Hopefully you'll just stop me, chat me.
Yeah, is that a C with the line all the way through it?
Yes.
Are you actually trying to make it look like an E?
Well, it's not an E, it's like a fancy, it's like a carved out, it's like a euro. Sort of. So it's like a C with a line in it. I can't remember what it's called. But yeah, so here, I'll clean this one up because it's not very good. It's as good as it gets. Hey, nice. Does the keyboard tell you what it's called, Riley?
Is there another? Sorry. Is there another way for using not a member of? Could you use like a different symbol before the E to be not a member of, or is it like always that way?
Sorry, I'm having a really hard time hearing you, but element.
Are you hearing me better now?
Yeah, try it. So ask me again.
Right. So I was asking if you could use another symbol to denote not instead of using a like a cross through the member of. Could you use like a negation sign or something to negate the?
So kind of like in programming, if you use like
Still there. Yeah.
you can okay, element set membership, awesome. You can, like, I'll understand, but when we write math, we usually do the strike through. Yeah. But I mean, I'll understand, but I know if you guys have Jim later for 251, he'll want the strike through. Stylized lowercase epsilon. That's a mouthful. Yikes. Good. At least we know it's sort of an epsilon, yeah. Stylized. So there are some predefined sets that we're gonna need to have a handle on, some more than others, right? And so we have some common sets of numbers. We have some common sets of numbers that already are defined. So we have some common sets of numbers. With their own notation. With their own, and I'll put in brackets reserved notation because we can't use it for anything else. Reserved notation. First up, the big player, the set of real numbers. So every number that you can possibly think of from negative infinity to positive infinity is a real number, right? You probably know that there are imaginary numbers, but we're not heading down that way. So we'll just be dealing with real numbers. And so the set of real numbers is this fancy R. So it's just an R with an extra back, I would say. Right? And so this is the set of real numbers all numbers from negative infinity to positive infinity. All our numbers are in the set of real numbers. Okay.
Another question.
Oh, sure.
Yeah. The backways E, is that the same symbol as the member of, or is it a completely different symbol? Like a capital backways. Back,
Oh,
yeah.
is in the set. No, they're I mean,
Yeah.
what?
Yeah.
Shoot, off the top of my head, it's in the set, right? It's in the set. I think you can use them interchangeably, but for some reason we don't.
Okay.
So I would say probably, and this is just because we're not introducing that notation today, so I'm on one track mind. I would say it has to do with an element in a set and then a set and its relationship. But I would have to, yeah, contains as member.
Okay.
Yeah, so I would say that they're interchangeable, just kind of off the top of my head.
Okay. Thank you.
Good. So it's just the other way. Thanks, Zach. Okay, so the set of real numbers, that's a big player, right? So yeah, well, Zach's bringing Wikipedia to us. So the set of real numbers, right, we'll need to have a handle on that. We've also got our fancy n, which also has another back, kind of, I don't know, it's hard to write, which is just our counting numbers, so our natural numbers. So that's going to be your set 1, 2, 3, 4. And then what we do is we can just do ... as soon as someone is able to pick up on what you're saying, right? So, okay, it just keeps following that pattern, 1, 2, 3, 4, 5, 6. Everyone knows what that means, right? And so then you can use the ... and so on, essentially. Right? But you have to establish a clear pattern. I can't just do 1, ... No one knows what to do next, right? So these would be our natural numbers or our counting numbers. Right? Next, yeah, 1. Exactly, not very helpful. We've got our whole numbers. Oh, I guess I should do a proper capital W. And pretty sure it's got the line here. It's just kind of like a fancy bold W. So that would be your counting numbers, including 0. So 0, 1, 2, 3, ... N and W, we're not going to use that much, right? It's good to have a handle on which one's which. But the one that I will use is Z, right? The set of integers. So that would be whole numbers from negative infinity to positive infinity. And so Z is going to be important. Z starts out here, and then I'll pick it up at -2, -1, 0, 1, 2, ... And this is the set of integers. Okay. So for us, right, if you have to remember only 2 of these from today, right, you need to know the set of real numbers and you need to know the set of integers. Right. We'll throw some more on there just for completeness sake. So Q is the set of rational numbers, and the Q is just kind of bolded on the outsides. So Q, now I'm going to use the curly bracket, but then I'm going to use what's called set builder notation. And so I'll write it out and then we'll talk about it. So we've got A over B, and then a vertical line, okay? And that's going to be read as such that, but I'll make a note of that in a little bit here, such that A is in the set of integers. B also has to be an integer, and B cannot be 0, because then you're dividing by 0, right? B's in the denominator. Man, it's been a long summer, huh? I always have to go numerators on top because it's numero uno, and then the denominators in the bottom because one of them has to be in the bottom. So I had to think, and I teach math, so don't feel bad or feel good if you have it under control. So this is the set of rational numbers, right? So fractions. What I've done here is used set builder notation. So we would read this as Q is the set of A over B such that A is in the set of integers B is in the set of integers and B is not 0. Okay. You can see why there's all this shorthand notation for all this, right? You don't want to be writing all this out all the time, right? And so we need to get proficient in reading this stuff, right? And so here, this vertical line, you read as such that. Let's just do a little reminder, right? We can't divide by 0, it doesn't exist. Your calculator will spew out an error, right? And so no dividing by 0, right? And so, but we have to say it explicitly that B cannot be 0, right? If it's in the denominator. So, just as another example here, in general, if we have the set of X such that X is an even counting number. So now I'm going to use the description method here in the set builder notation. So X is an even counting number. Not a very nice curly bracket, even worse. Oh, well. this is the set of all x such that x is an even counting number. Such that x is an even counting number. So as we see more and more kind of set notation, all this stuff will just kind of come naturally, right? But if it's the first time that you're seeing it, then just give it some time and it'll come. Right? So we say that two sets are equal, right? Just as, you know, two numbers are equal if they're the same, right? So kind of a no-brainer here, but two sets are equal. Two sets are equal if they contain exactly the same elements. Exactly the same elements. So I'll underline the definition here, or the defined word, I should say. So if we have something like the set E, E is the set 2, 4, 6, 8, ... Even counting numbers. Then we can say that the set X, such that X is an even counting number, right, would be equal to the set E. Such that X is an even counting number is equal to, and I'm running out of room here, so I'm just going to scoot this over just a smidge. Cheating. Is equal to the set of x's such that x is in the set E, right? Just a fancy way of saying it's equal to E, right? But I'm just matching the notation, that set builder notation. So that's if two sets are equal, right? Then they're exactly the same. All the elements are exactly the same. Two sets can be equivalent, right? But that doesn't mean equal. Equivalent is actually just very big. So two sets, oops. Two sets are equivalent if they have the same number of elements, right? So that's pretty basic. To be equivalent, all you have to have is the same number of elements. And so two sets are equivalent if they have the same number of elements. And it's denoted using this kind of double-sided arrow. I should clean that up. Double-sided arrow. Hey. It's as good as it's gonna get. So if I write A is equivalent to B, that means that they have the same number of elements. It doesn't tell me anything else. And I'll underline equivalent because that's what we're talking about here. So hey, these don't look the same at all. Close enough. So A is equivalent to B is red. A is equivalent to B. Only talking about the number of elements. And so the number of elements in a set is called the cardinality. So if we talk about the cardinality of A, right, then it tells us the number of elements, the cardinality of B. If the two cardinalities are the same, then they're equivalent, right? And so we'll start building on all these definitions. So the number of elements in a set is called its cardinality. Cardinality. The cardinality of A is denoted by A essentially with absolute value brackets around, right? Two vertical lines on each side, or one on each side rather. Okay. So if we have something like, so if the set A is 2, 3, 4, 6, for example, then the cardinality of A is 1, 2, 3, 4 elements. So the cardinality of A is 4. Let me underline. There, cardinality. Okay. Next up, right, so we've talked about equal sets, right? Then they have exactly the same elements. We've talked about equivalent sets, so they have the same cardinality, cardinality being the count of the elements in the set, right? We're also going to talk about the universal set or a universal set because it depends on what you're talking about. And then we'll also talk about the empty set, which has no elements. So these are all things that we need to know about. So a universal set which is denoted by U, of course. So U is taken, right? If you're trying to name your sets, there are some letters that you can't use, U being one of them, right? And those fancy letters that we had, but I don't think you were going to try to use those. But U is used for the universal set, so it's reserved. So a universal set U contains all the elements under consideration. So it depends on what you're talking about, right? And so if you're talking about all the letters in the English alphabet, right, then you've got all our letters, and that's your universal set. Okay. all the students at Okanagan College would be your universal set, right? And then you can pull subsets from there. And so a universal set, U contains all the elements under consideration, all the elements under consideration in a given discussion. So it depends on what you're talking about. In a given discussion. So that's the universal set. Then there's the empty set. So a universal set can change, right? So it depends on what you're talking about. Are you talking about a deck of cards? Are you talking about students at the college? Are you talking about, I don't know, dog breeds, right? So the universal set is going to change, but the empty set is always just the empty set. There's only one, right? Because there's only one way to be empty. So we say the empty set which we denote by 0 with a diagonal line through it, right? Or an empty set. I will always use the 0 with the line through it, right? Kind of the nil. So if that's how you write your zeros, you're gonna have to change your ways because that's how my mom writes her zeros. Empty set, 0 is not the empty set. 0 is a number. Okay. So the empty set, which we denote as a 0 with a line through it, right, contains no elements. Contains no elements. So here, I just want to make sure, right, if we talk about, so notice that this is the empty set. Right? So 0 with a diagonal line through it, that's the empty set. Zero is just a number, right? So it's not a set. We could also do something weird, like a set of the empty set. A set of the empty set. Or I should say containing the empty set. So a set containing the empty set. So now, just so we kind of get our juices flowing here, right? If we're talking about the cardinality, right? The cardinality of the empty set is going to be 0. Right, there are no elements in the empty set. The cardinality of a number, right, is not a set, so we can't take the cardinality. So here, if we're talking about cardinality of these things, right, the cardinality of the empty set is 0, right? But the cardinality of a set containing the empty set is 1, right? It's got one element and it's the empty set. So we have to be really, really careful and really, really nitpicky. I don't know if you have had one of those math teachers that's like very, very nitpicky. Well, you didn't say that exactly. And I know what you meant, but it's not what you said, blah, blah, blah. Anyways, that's me, but you'll be there soon, right? You have to be very careful with what you're saying in math. Like English, you can just say whatever you want. Right, so we have to be very, just slow down and read exactly what it's saying, right? So, and we can't take or find the cardinality of 0 because 0 is not a set. Can't find cardinality of 0 since it is not a set. It's subtle, but I have a line break there, so I'm just trying to work, or a page break rather, so I'm just trying to work it on the same page. More for me than for you. Good. Yeah, so the empty set can be a little bit tricky, right? But it is just a set with no elements, so, but it is a set. Okay. And of course, as you might have guessed, right, we can make sets of sets, right? So we don't just have to have these bare elements in there. We can make a set of multiple sets and kind of balloon out from there. But before we do that, not today, we're usually wanting to visualize these sets, right? And so that's where Venn diagrams come in. Pretty basic, really great for jokes and stuff. And so we use them a lot. And I think we all just kind of know if I draw something like this, right? Here I've got A and here I've got B. This would be a Venn diagram, right? So I'll remove this here. I'll draw a nicer one, but that's a Venn diagram. So that's where we're headed next. So we often visualize sets, and I would say and their relationships, right? So we often visualize sets and their relationship make it plural, relationships. Because we could have more than one or two sets. Using Venn diagrams. Would the cardinality of two sets be 2 or the total number of elements in both sets? It depends on how you've defined it. So if I say, okay, A is the set of 2 and 4, B is the set of 1 and 3, then it depends on if I'm defining C is the set of A and B, then I would say the cardinality of C is 2, right? And we're going to talk about the union and the intersection in a few pages. And so then we'll talk about how we combine these two. So if we or if C is A and B, it would have to be or, but we'll get there, right? Then we would have, I should say or, A or B. Then the cardinality of C would be 1, 2, 3, 4, so 4. It depends on how you find it. Yeah. Oh, was there a question? Oh, just hearing things. Cool. I'll remove this here though. But we will get into combining sets in a little bit. Good. Okay, Venn diagrams. The outside is usually a rectangle, right? So the outside of a Venn diagram, and we always start with a rectangle, and that denotes the empty set, or impossible, the universal set. So a Venn diagram has an outside rectangle representing the universal set. Don't want to slip up again. Representing the universal set, right? We want to show all the possible things that we can pull from, right? And that's our rectangle. So if we have something like, now I'll draw my beautiful, well, not so beautiful rectangle. If you want to, you can put a little U up here. Often we put it in the top left-hand corner. But it is understood that the rectangle is the universal set. So then if we have something like, if U is the set of counting numbers up to 9, so 1, 2, 3, 4, 5, 6, 7, 8, 9, and the set A is the set of 1, 2, 3, ding, ding. A is in the set U, right? So making it a subset of U. And of course, all sets are pulled from the universal set. Okay. But how we would denote that up here is I would just draw, and Venn diagrams are just for visualizing things. So sometimes they don't necessarily match what you're going to be looking at. I've got an example coming up here, but for now, I'll just do A in here, right? So usually I have a little circle. So here I've got A, and A has 1, 2, and 3 in it, right? Whereas all the things I could have chosen from were 1, 2, 3, 4, 5, 6, 7, 8, 9, right? And so 1, 2, and 3 are in the set A, so I don't need to list them again. And in fact, I shouldn't list them again in the universal set, but here on the outskirts, do a different color here. I've got 4, 5, 6, 7, 8, and 9. So it's kind of a basic Venn diagram. But we're going to use them to look at relationships between 2 or more sets. Any overlap, or if they're not overlapping at all. So here, right, on the outside, just shade it in, right here, we've got all these elements that are not in A. Right? And so we call that the complement of A. So all the elements that are not in A, but are in the universal set, they're the complement of A, and they make up their own set. So the set of elements not in A is called the complement of A. Is called the complement. Complement, not complement. Although that'd be cute. the complement of A. Denoted by A with a bar over it. All right, so A with a bar over it or an overbar is the complement of A. So in this case, the complement of A, right? We can list those numbers. We already did 4, 5, 6, 7, 8, 9, right? It's everything in the universal set that's not contained in A. So
And
here,
everything in the universal set is every other number besides 1, 2, 3, or just what is listed 4 through 9.
So the universal set is all set of numbers, and then the complement of A is everything not in A. That answer the question.
So what numbers are in the universal set?
So the universal set in this case is 1, 2, 3, 4, 5, 6, 7, 8, 9. So here we've defined the universal set first.
And then the complement of A is 4 through 9?
That's right.
Okay, thank you.
I thought you told us we can't use U for our sets.
Well, because I'm calling it the universal set. So I've reduced my universe to only include 1, 2, 3, 4, 5, 6, 7, 8, 9. So in this case, you are allowed to use U, but only to denote the universal set.
Will there ever be a time where the universal numbers aren't stated?
Yes, I could say something like the universal set is the set of integers, for example.
Right,
Okay.
so then it would go to infinity?
Exactly.
Okay, thank you.
So, good. So the complement of A, if we're listing it, right, is going to be the set of 4, 5, 6, 7, 8, 9. So the universal set changes depending on what you, exactly, yeah. So the universal set is gonna kind of morph depending on what you're talking about. Yeah. So in this case, we had this itty bitty universal set. The universal set could be things like a deck of cards, if you want to get kind of abstract. Right? We've got 52 cards, different suits, different colors, different numbers. I'm like, there's another thing going on there. Good. So then what it looks like, right, is you would have your universal set here, and I'm not gonna do the U because it's understood, right? So it's okay to drop the U with your Venn diagram. If it helps, sure, put it up in the right-hand corner. But you don't have to. So if we've got the set A here, everything on the outside is the complement of A. So usually we use Venn diagrams to talk about more than one set, right? So we talk about, we'll start with 2 sets and then we can easily move to 3 sets. It gets a little hard after 4 sets because then you've got 4 rings with lots of overlap, right? And so I'll put it on a new page here. If we have 2 or more, 2 or more sets, put the or more in brackets. Let's call them A and B, right, for simplicity. We can discuss their relationship, right, in terms of subsets. And so we can discuss their relationship in terms of subsets. All right, so now we're moving into subsets. Of course, we kind of saw where this was going, right? And so we can write something like A and then have a C with a line underneath. Or sorry, is a subset so it's just a lowercase c with a line underneath. Is a subset of B. So what that would look like, right, in a Venn diagram, if A is a subset of B, right, it means that all the elements of A are contained in B, right? Just like all the elements of A were contained in the universal set, right? The universal set is our biggest possible set, and then we'll have subsets kind of rolling down from there. So what this means is that every element of A is also in B. What that looks like as a Venn diagram is if I've got a big circle called B, right, that's my set B. It's a subset of the universal set, right? So it doesn't necessarily have all the items or the elements in the universal set, but then I've got a smaller circle. Maybe I should do a different color here. How about that? A. So all the elements of A are contained in the set B as well, right? So they're all overlapping from A to B, but not the other way around, right? There are elements in B that are not in A. And of course, you can write them vice versa and switch them up. But this is if A is a subset of B. Another relationship, so I'll start numbering. We'll talk about just 3 relationships. There's really only 3 possibilities of relationships between A and B, right? Either A is a subset of B, A could be equal to B, right? And it's, why is the line below the subset symbol? I don't know. I think it's just notation. So we just kind of go with it blindly. But yeah, so is a subset of is just the C with a line underneath. And yeah, I don't know why there's a line under. Second relationship is if, cool. C with a line above is shorthand for with, yeah, that's true. Which is also kind of weird. Our second relationship, whoops, I zoomed in there. Is if A is equal to B, right? then we have two equal sets, meaning all the elements are the same, right? And so how would we denote that in a Venn diagram? Well, we would just have pretty much one circle with A and B because they all have the same elements. So that's if you have equal sets. And then finally, our third relationship is going to be if A and B are disjoint. So disjoint meaning that they have no elements in common, and so there would be no overlap in the sets. So A and B are disjoint if they have no elements in common. If they have no elements in common. And I'll underline this disjoint because that's something that we should be aware of. Right, you might have heard of things being mutually exclusive, right? Just kind of, they have no elements in common. Nothing in common. And what that looks like in terms of a Venn diagram, you'd have A over here, and maybe you'd have B over here. No overlap, right? No elements in common. Time for an LFF. Little fun fact. Little fun fact. The empty set is a subset of any and all sets, right? So if you're listing subsets, the empty set will always be a subset of whatever you're talking about. Right? Little fun fact, an LFF. The empty set is a subset of every set. Say that 3 times fast. The empty set is a subset of every set. Huh? Every triangle is a love triangle when you love triangles. Love it. Yeah, pretty much. So let's do a little example here, just a quickie. So, because we've just talked about definitions, blah, blah, blah. But if we let the set C have 5 and 7 as its elements. Find all possible subsets. Let you noodle on it, just briefly.
Emily,
Yes?
would the order of the elements matter?
No. So 5, 7 is the same as 7, 5. Good. In fact, that's a pink note. Order does not matter. Thank you. So our possible subsets here, right? We only have 2 elements, so we can kind of break them down. But if I'm listing all the possible subsets, right, the first one, I don't want to forget about the empty set, right? So the first one I'm going to jot down is the empty set, because that's probably the one that you're going to forget, right? But the first one is just the empty set, or I prefer the 0 with the diagonal line. But in keeping with the set notation, right? So that's a subset of our set C. The element 5 on its own, right? That's a subset of C. The element 7 on its own, that's also a subset of C. And these are all subsets. And then finally, right, along with your empty set, a possible subset is always going to be the set itself, right? If the 2 sets are equal, right, A can still be a subset of B if they're equal, and vice versa, right, because they're the same. And so the set 5, 7 the set itself will always be a possible subset So for a lot of the exercises in the homework, right, it says, okay, you got to list all these subsets. So just as a check-in point, right, you want to have the empty set for sure, and you want to have the set itself, and then you can get to work on breaking down into smaller subsets. Right?
Emily?
Yes?
So for this example where C equals 5 and 7, including the set itself, like that's just specifically with C equals 5, 7. It has nothing to do with any other relationship from any other kind of set.
No, just 5, 7. So if
Right.
we're focusing on C, is essentially our universal set, just being 5 and 7. That's all that we're talking about here. For this
So in this case, the C is the universal set, which we narrowed down to 5 and 7. And the subset is just 5 and 7. Like I'm just not sure why the whole set in itself would be a subset. Like subset usually seems like a portion of its previous state. So
yeah, so that's the sneaky part, is that the subset could take up the whole. So if you're thinking about a Venn diagram, right, the subset can take up the whole circle. So if you have, your Venn diagram here, and you've got C here, and C is 5 and 7, this whole thing could be a subset. They're equal, right? C would be equal to this new subset, but it is technically still a subset.
are there any like specific examples like when that would be a thing that you'd actually see, or is it just like a math like rule that it's included?
Yeah, it's just one of those things. So a possible subset will always be the empty set, which I think we're kind of all on board with. It's kind of easier to think, oh, well, you could have no elements, fine. But then also we could have the entire set as a subset. Oh yeah, so Zach says subset is less than or equal to. Yeah, kind of. So it's got that kind of inclusivity as a possibility. But
Thanks.
I know. We just need to remember, right? Always include the empty set, always include the full set itself. But yeah, you can think of it as the inclusive in the less than or equal to type of situation. Cool. What we want to talk about, and there's a name for it, is a proper subset, right? So a proper subset are all the subsets that are not the set itself, right? So I don't know if we call them improper subsets, but sometimes there's not the opposite, right? We say proper subsets are all these subsets like the empty set 5, the set of 5, the set of 7, those would be proper subsets. And then the set of 5, 7, which is just the set itself, would not be a proper subset. Right? So we've got terms for all of it. So a proper subset is a subset that is not equal to the original set. Is a subset that is not equal to the original set. And I'll do here a proper subset. But then we change our notation, so it is kind of inclusive, exclusive in a way. So you have A is a proper subset of B, denoted by A is, I'll bump it down. Just the C, so no bar underneath. It's different than the inclusive, exclusive, but it's okay. It helps to think about it. And of course they're related. So it's just me being nitpicky. But yeah, so a proper subset, you would ditch the line underneath the C and just have the C. So A, I usually end up reading it as is contained in B, right? The little C contained. But it's technically a proper subset of B. And I'll make this a potentially nicer looking C. Not really. If A is a subset of B and A is not equal to B. So if A is a subset, can only be a proper subset if it's an actual subset of B. Subset of B, and A does not. A is not equal to B. And then what would be the difference between the two subset symbols? So this little guy here is for a proper subset. So here you're defining that it can't be the same as B, right? A is all contained inside B, but it's not equal to B. Whereas versus this subset, so it's just a general subset, so it can have B as one of the options, right? A equal to B as one of the options. So this is all subsets. Good. Hey, I have a note here. It is called the improper subset. Phew. An improper subset of A is the set A. It's still a subset, but it's an improper subset. So A isn't equal to B, but contains the same numbers. That's right. So do I have a quick example? If A is the set of 2 and 5, and B is the set of 1, 2, 3, 4, and 5, then we would say that A is a proper subset of B. It's also true, or A is just a subset of B. So it just depends on if you want to highlight that it's a proper subset, or just it is a subset, it's still just a subset of B. Proper subset versus just a subset. Okay. So let's see here. How about we do a little example, right, where we're going to list all the subsets. So if we let A be the set of 4 numbers, 2, 4, 6, and 8, I want you to just take a quick little minute while I write out the question to find both the proper and the improper subsets, as well as the cardinality of A. So just write it out. Find the proper and improper subsets of A and the cardinality of A. So is the improper subset the one with the line? The improper subset is when they're equal to each other. So that would be if A equals B. Because that's when the subset is equal to the full set.
Okay, so the example up there was A being a subset of B, or you showed me 2 different subsets there. Which of those 2 are the improper subsets? Or is the improper subset?
So in this case, with A equal to 2, 4, 6, and 8.
No, in the example you have just before that with the blue writing there. Yeah, which of those are the proper and improper subsets?
Here we go. An improper subset of A is the set A itself. So neither of those would be
Improper.
the C with the line underneath
Right.
includes the improper subset.
Okay, that was what I was asking. So okay, so the C with the line underneath is the improper subset.
It includes the improper subset, but also all the other proper subsets.
Also, so the C with the line beneath is like a combination of all subsets.
All of them.
Okay. All right.
So if you have like here, the C with a line underneath, right? That's your subset. And it could be broken down into the C, which is a proper subset, or the equal to, which would be the improper subset, right? If the two sets are equal to each other.
So basically, if you just, you know, referring to any subset, you can just use the C with the line beneath. But if you're specifying just one, if you're specifying the proper subset, then you have to use it without the symbol, without the line. Okay.
So the C with a line underneath is what you'll see most commonly used. Yeah. Okay, so our improper subset, well, there's only one, right? When the set is equal to A. And so the improper subset, we'll start there, is the set 2, 4, 6, 8. Now for our proper subsets, right? That's everything kind of less than A, I guess. So for our proper subsets, I'm always going to try to start with the empty set, right? I might forget, but for our proper subsets, I'll do the empty set, always an option, right? Or if you prefer just to have the empty curly brackets are really fun to draw, so why not? And then we can break it down, right? We can have each individual element 2, 4, 6, 8. Curly brackets are also easier to type. That is also true. Yeah, they're the defaults. No square brackets here. Yeah, so yeah, definitely easier than the empty set. So that's probably why they do it, actually, now that you mention it. We can do each individual element, but then we can also do combinations of those elements, right? As long as we remember that the order doesn't matter, right, we'll be able to kind of plow through, and there's going to be lots of different subsets or possible subsets in here, right? So we'll start with the empty set, and then I'm going to give myself lots of room here. 2 on its own, 4 on its own, 6 on its own, 8 on its own. Ugh. The combination, so now I'm moving up in 2s, right? So 2 and 4, 2 and 6, 2 and 8. So I've got 2 and 4, 2 and 6, 2 and 8. Then I'm moving to 4. I could have the combination 4 and 2, but I already have 2 and 4, and since the order doesn't matter, I can skip that one. Right? Then I've got 4 and 6, and then 4 and 8. Right? So you want to kind of keep your eye on the prize here as you work through all these. Right? So 2 and 8. Next up, 4 and 6 we said, because 4 and 2 is essentially already covered. 4 and 8. 4 and 6, 4 and 8. Next up, I'm going to the 6 first. 6 and 2 is already covered. 6 and 4 is already covered. 6 and 8, my only one's missing, right, for the combos of 2. 6, and 8. Combos of 3. Uh-oh. Here we go. I'll take it easy. 2, 4, 6. And then I'm gonna change up my last digit. So 2 and 4 are gonna stay the same. And I'm gonna go for a 2, 4, 8. Okay. Now I'm gonna move to start with the 4. No, I confused myself. 2, 4, 8. And then I'm done with the 2, 4 combination, so now I'm gonna move to the 2, 6 combination. I have to do it kind of to follow. As long as you can list them all, it's fine. But it's hard, it's really hard. 2, done with the 4, 6, 8. Okay, now 2, 6, 8. Now I'm going back to, I'm done with the 2 first. I'm done with the 2, so now I'm on 4, 6, 8. Painful. Yeah, it is. I know. 4, 4. I'm like 2, 2. 2. Anyways, here they are. All our possible subsets. Proper, improper. There's only one improper, right? Sure, this one. So how many subsets do we have? We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 subsets, right? So we have 16 possible subsets. (16 subsets. All right, we'll make a note of that. I also asked what the cardinality of A is. Oh, finally, back to basics, right? How many elements in A? There's 4 elements. 1, 2, 3, 4. Great. The cardinality of A is 4. You could make sets of the different cardinalities if you have different sets, and make a weird other set, right? And so all these things just kind of run together through the hills. So for you guys especially, right? I know that you deal with a lot of, okay, well, how many combinations can I have, right? And so just as a rule, right, however many elements you have in your set, there's going to be 2 to the power of that many elements, different possible subsets. Okay? So a set of size n, lowercase n is usually what we use to denote some sort of size. A set of size n has 2 to the power of n subsets. Just because that's good to know, right? Especially if you're asked to list all the subsets, you'll probably want to know how many you should be going for, right? So you count the number of elements and then 2 to the power of that. So 2 to the power of 4 in our case, right, is 16. And so that's why we had to get to 16. So it's just kind of a nice check-in point too, to make sure that you've captured, got to catch them all those subsets. Mm-hmm. Good. So many sets, Are we ready for operations with sets? We're doing it anyways. I'll start a new page. But any questions about this? So just sets, subsets, just kind of practice. But a lot of terminology, right, that we probably haven't seen necessarily yet. So we have to get to that.
So you can always determine the amount of improper sets by 2 to the power of the cardinality?
Yeah, so it's going to include all the possible subsets. So in this 16, we included the improper sets or subset. So it's all the possible subsets.
Including proper, improper. Okay.
Is
So-
there only ever one improper subset?
Yes. Yeah, because it's just the subset that's equal to the set itself. So that can only happen once.
Oh, okay.
Nice. Good. Good. All right. Fresh page here. Holy smokes. What time is it? 2. Am I running out of time? Just blah, 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 blah. All right. Well, I've still got a little bit of time. Sorry, guys. I was like, oh yeah, this will go so quick. What am I going to do with the rest of the time? Let's just talk briefly about operations with sets, and then you'll be, oh, awesome. So the improper subset is the subset with all the elements, exactly. Good. At least I caught myself running out of time before I ran out of time. That's something. Operations with sets. Right. We'll at least get started on it so that you can get kind of working on the 2.1 homework and the 2.2 homework, which will be part of your assignment marks. So there's the intersection of 2 sets and the union of 2 sets. And so those will be the operations that we're going to focus on mainly. And so the intersection of sets A and B denoted by A and then an upside down U, which this upside down U is the intersection, but you can read it as and, right? And so how I kind of visualize it is the upside down U, I just put a bar in there, and then it makes an A, and then it looks like an and, right? And so it's A and B is the intersection. And so the intersection of sets A and B is the set that's common to both of these sets, right? So it's the intersection, right, where they overlap. And so we have is the set consisting of all elements common to A and B. So what does that look like? We can draw a Venn diagram. Can put my U there, I don't have to. If I've got a set A and the set B, where they overlap, that's my intersection. So here, this is A and B, or the intersection of A and B. Whereas the union of the sets A and B, the union is going to be just an upside, well, a proper side U, right? So it's just a capital U. So the union of sets A and B denoted by AUB, U being the union, oops, I almost said intersection, that'd be confusing. But you can read it as or. Is the set consisting of all the elements of A or B, or the shared elements as well, right? So the or is the whole kit and caboodle, all of it. So is the set consisting of all elements of A or B or both? Okay. So in terms of a Venn diagram, what does that look like? It means I've got A here, I've got B here. And it can either be an A or B or both. So this here is A union B, or just A or B is how you can start reading them. And I'll underline here, the intersection is A and B. Oops. Whereas the union is A or B. Okay. We do recycle that capital U, but the context will tell you whether it's the universal set or the union, right? And so there shouldn't be any confusion about that, but if there is, you can always just ask. I guess I'm out of time before I can't start another blurb here. But that's good. We'll start with an example next day. How about? Are there any questions? Oh. All right.
The union includes the intersection?
That's right.
Okay.
So it's A or B or all the intersection as well. Nice.
Thank you very much.
Awesome. All right. We will start with an example on this next day. Cool. See you guys on Wednesday. Peace.
See you Wednesday. Thanks.
See ya.